So it's nice to be the lecturer in the James Spence series, to be the first one. I knew him, John Spence. I knew him from coherent diffractive imaging. When I first met him, I didn't know it even existed. I didn't know anything about synchrotron physics, free electron physics, or anything like that. And really, he was the person more than anyone else that explained it to me. So it's the second time I've been here in Tampa. It's the very second time. I was here in 2019. And of course, he was here as well at that time. So it's nice to come back for a second time. So I tried to make this a introductory lecture, but I knew that many of the people in the audience would also know some of the things that I talked about. So I'll try to end up the talk with some new science, some new physics that we've been just looking at. But I hope I'll try to make everything understandable to everybody in the audience. And so I'll try to do that as I go through. So first, I thought I would talk about magnitudes. So we all, everywhere in the world, everybody knows, even way outside of physics, they know what a nanometer is, or at least they know it's very small and very short. I think it's a stand-in for something short. People talk, will be see you in a nanometer and so on, or about this is nanometer scale or something like that. So an attosecond is to a second much shorter than a nanometer is to a meter. One is a billionth of a meter. One is a billionth of a second. Now, a second and a meter is not the same thing. Of course, I know that. It's very different. One's the space and one is time. And so it's not the same, but maybe to our sense of it, they're sort of the same thing. One is meters a reasonable distance on a human scale, sort of the distance we walk when we move our feet. And a second is a reasonable time on a human scale, maybe kind of fast, maybe a little faster than a meter would be in a second on a human scale. But the attosecond is really much shorter compared to a second as a nanometer is to a meter. So maybe you should first ask, why should we care? Why do we care at all about something so short, so small? It's way different than our ordinary lifestyle. So electrons are sort of the glue that hold matter together, okay? They drive chemistry, because everything in chemistry is really about electrons, about the bond that you make. They drive electronics, they power photovoltaics, and they power many other things in our modern world. And so we should care about them for that reasons. They don't weigh very much. The forces within an atom or a molecule or a solid are very, very strong. And so they don't weigh much. And you're really pushing them hard, so they move fast. And distances are very important. Small distances are very important. You go from one atom to another, that's a big change in the local environment. And so we should care about them because they do things very fast. They do it very fast for all three reasons that I say. So I give an example. It takes 150 attoseconds for an electron to go around the hydrogen atom. So maybe you could say that's roughly the time scale it would take to form a bond. And if we're talking about a hydrogen, involving hydrogen. Probably the maximum speed of electronics in general, probably the maximum speed would be the speed at which electrons can rush in and fill in some sort of a hole from all kinds of directions, and it's probably around 20 attoseconds. So we're almost there in the ability to make short pulses, and after that, there are faster things, but maybe they won't be so important to us. The nucleus, there are things that happen in the nucleus much, much faster. And of course, ultimately, probably we'll want to measure them, but they will not affect our daily lives in the same way, I don't think. So now I would like to take just 1 minute to talk about the basics, and then I'll jump from the basics to something to do with attoseconds themselves. So behind me is a sketch of what a pulse might look like. So a pulse is made up of many different frequencies, which means many different wavelengths of light or many different colors of light. It's always made up of many different frequencies. But the frequencies are synced together so that someplace along the line, all bumps like this add, and all dips add. And so we have something that looks like an isolated pulse in the center, and then they don't add so well, and then they don't add so well, and they don't add so well. And then if there's many of them, they don't add at all, and you don't see them. So a pulse is just an interference in time, a constructive interference in time. Um, so you can see right from this picture some things about it. So you can see that the duration, the minimum duration of the pulse, is going to be something to do with the duration of the cycle of light and how it goes. And so that's true. The minimum duration of the pulse is basically one cycle of light of the average frequency that makes up the light. I kind of think of it, you can think of it like a rogue wave. A rogue wave is when waves come all together and they happen by accident to add up and become really strong, and the ship is wrecked by the fact that the rogue wave came through. And so because this is an interference, just like a rogue wave, doesn't mean it's not important or that it doesn't modify materials or it doesn't do something really significant or we can use it. It's just how it's made. Okay? So now I'll show you how this is made in ordinary attosecond science in the model that we talked about, that was talked about in the introduction. So put on your first year physics hat, just a freshman physics. The only thing you know is classical physics, F equals ma. And you can understand this full graph. I won't put F equals ma on the board, but you can keep it in your mind and I'll talk about it sort of like F equals ma. So we take an atom, you see it in A over there, see an A. We take an atom and we irradiate it by a laser field. So laser field is just a wave of laser light coming out, and we can make laser light really, really prominent, really bright. And so let's imagine it's so bright that pulling on the electron, it pulls it free from the atom. And so that's the first step. Of course, it happens when the field is strong, when we're right near a peak. And so it happens around the peak, somewhere around the peak. And it depends on when it happens. So it will happen in all of these times. In quantum mechanics, each atom happens all of the time. But you might think of it, some atoms it starts early, and some atoms it waits for the peak, and some atoms it goes by the end. You know, it's just this electron that's jiggling around in the atom, and it finds a hole and gets out. Okay, so that's the first step. The electron gets out. Once the electron gets out, it's pulled by the field and it picks up momentum. F equals ma, picks up momentum just like that from the field. Just gets pulled by the field. Just imagine, you can think about a wave if you want to go down to the lake down here and think about a wave and something popping up and down. And it's not much different than something popping up and down in a wave, a cork or whatever it is. Okay? And it picks up momentum as it moves away, and of course, as the field changes. So the field goes through its maximum and comes down again, and you can see that being illustrated in the yellow. The yellow part is the field, okay? And so, of course, the field will go through a minimum, but the electron's got lots of momentum by this time, especially if it's born after the peak of the field. And so it keeps going for a while, F equals ma again, and then eventually it turns around and is pulled back towards the ion. Now, depending on when it's born, it might come back and bang into the ion and might not come back and bang in the ion. If it's born late, if you do F equals ma, just go back home and do it, first year physics, you'll find that it collides kind of early, not too much energy. I represent it by red up here on the curve. If it's born a little earlier, it comes back a little later with a little more energy. I represent it by green up here on the board. And if it's born in the optimum time, which turns out to be 17 degrees after the peak, it's born in the optimum time, it comes back just about the zero crossing of the field. It's just about ready to start pushing it the wrong way. So that's the optimum time. And it comes back and it gives high energy pulses. Okay. So this idea is recollision that you heard about in the introduction. It's recolliding with the ion from which it left. The electron is recolliding, and when it recollides, it has a chance of moving down and just recombining to the atom from which it left. And in that recombination, it gives out light, and that light is the attosecond pulse. Now you can see a couple of things about this light. First, you can see it's chirped. It starts red, then green, then blue. And so it's organized and we can deal with it. And we can put all colors just one on top of the other if we want to, just like I showed you in the last few graph. But we need something that slows down the red and speeds up the blue. And it turns out we can do that. We can, and the red, green, and blue are stand-in from UV, VUV, and X-rays. And so it turns out we can do that, and we can find it, and that's how you make the shortest pulses. The shortest pulses are about 40 attoseconds now. So that's done by simple F equals ma, and I need something that you can't know from F equals ma. I need something that's dispersive. I need a dispersive material. But we found first dispersive materials. So if you probably accept that we have them and we can just put beam through, and it just gets all the speeds right, and so they're all superimposed. And so that's how we make 40 attosecond pulses. It's really simple. It's discouragingly simple. It's so simple, really. So, but that basic idea, seeing high harmonics from at atoms, just like that, rare gas atoms that was used, was what got Anne Lullier, 1980. Oh, she did it in 1988. That's correct. And it's what got her the 2023 Nobel Prize. Okay, so that's Anne Lullier's contribution to see that experimentally. Um, So I just reinforced what I said all along. To understand the colors and to understand the timing of each color, you just need F equals ma. So I guarantee you, first year physicist and maybe high school physics could do it in an hour. I guarantee it. So, but remember, the electron is a wave. I show it as a particle. I show it as a particle, but it really is a wave. It has this sort of duality to it. It's partly a wave and partly a particle. The wave is the probability wave. It's a probability wave that it took this path and it takes all of these paths, and so it makes up a wave, and it's partly left behind as well. So remember, the electrons are a wave. It's a probability wave. So the recollision wave must interfere with the ground wave or the bond. How could it not, right? If it's given it's a wave and it's a probability wave, some piece of it's left behind and some pieces will come in. And when two waves overlap, they interfere. That's how we made the attosecond pulse in the first place. So attosecond pulse generation is the colliding of the bond with the recollision electron. That's a different way to look at it. I'll show you a picture just in the next few graphs about that, and so you really will understand it. But when the two collide, they interfere, just like we talked about interference before. And that interference is associated with the charges going back and forth. And so you can think about it in Maxwell's equations. Accelerating charges give you radiation, and you can understand the radiation in that kind of qualitative way. Okay. So it gives out radiation with the oscillation frequency that the interference has. So here's a photograph, or here's an illustration. So underlying is a Gaussian. So we assume it's a Gaussian wave packet. I'm going to show you in a minute what happens in a nitrogen molecule where it's a nitrogen bond, where it's a sigma bond in nitrogen. Okay, I'll show you what it's a nitrogen, but you can think about it as I go through. Okay, so there's two images here. The wave packet, which you see the wave coming. The wave packet is on one side and the other side, so the time is moving on just a little bit between it. When it's in one side and I got interference, I have constructive interference on one side, and I have destructive interference on the other side. And when the wave goes forward, I have changed where I have destructive and destructive interference. So that's the oscillating charge. The oscillating charge is the peak you see going through. That's the wave function, and the wave function squared is in the bottom. And so wave function squared, it is the probability of finding the electron. So it is the electron. So we have the wave function squared. Excuse me. Now, I've described this as if it were one electron. And so in some ways, that's the power of this kind of physics. You can think about it as if it's one electron, but it isn't really one electron. It's you take a gas of electrons, a whole bunch of them, or you take a solid, or there's many different things you can take. Now, I'll mention that a little bit longer, a little bit later on. So high harmonic generation, which is the radiation that we produce and that we use to make an attosecond pulse. High harmonic generation takes many atoms. So you have an atom here doing what I've told you, and we have another atom over here, and another atom over here, and another one here, and another one up there in front, and so on. And all of them have to radiate together in order to get a significant pulse, a pulse that's strong enough to do experiments with. That's called phase matching. So when we do it, what's really important is the electron comes back and recombines to the ground state from which it left. So the details of this, what the wave function really looked like, what phase it has, all of that cancels out because we go back right down to the ground state from which it left. It's that interference again, really. It's that interference again. This is the thing that will allow us to get the interference perfectly. So, so the reason that we can get a significant output, maybe not as much as a free electron laser, but this is a beautifully controlled situation. The reason we can get it is because we do it with a large group of atoms. If there's too many atoms, then we have troubles because as we ionize, we change the medium behind it. It was atoms in the first place, and pretty soon it's a mixture of atoms and ions, and so it's a plasma of sorts, which has different refractive properties and destroys phase matching. And so that's what happens, and that gives you the maximum field, okay? So now you understand pretty well everything there is to do with attoseconds. So let me just summarize so far. So we understand the essence, I think, of high harmonic generation from classical physics, from first year physics, I really think. With only a small ellipticity, this is not something I told you, with only a small ellipticity, the electron misses. So ellipticity means you got a little bit of acceleration off to the side. And so the electron, instead of being a fountain that goes up and comes back and hits the ion, is a fountain in a wind that misses the ion. And so only with a very small amount of ellipticity, the electron doesn't collide. And so we get no emission. And so one way to make sure you get a single attosecond pulse is to put some ellipticity on it or put time-dependent ellipticity on it. It's one way to get it. So with only a small amount of ellipticity, the electron misses, and you can do that with F equals ma too. So first year physics. Measurement of the pulse duration is almost the same as creating it. I'm not going to spend hardly any time on measurement, but you can do it if you want to. Think about photoionization with a pulse that's an attosecond pulse. And I create a photoelectron is going to go away at the first, at the middle, and at the end of the pulse, slightly differently, slightly later at the end than the first. And then I put a time-dependent field here, and I just streak it, right? And the one that gets first is going along a little further. Or maybe I can give it a little more energy. I can do it polarization this way, or I can do it perpendicular. Both ways work. But most people do it parallel. And so I characterize the energy or the angle if I know the field that's doing the deflection. So that's how measurements are made. I didn't want to spend a lot of time on it. Phase matching is transient because we transform the medium from an atomic gas to an ionized medium. And then it's like having second harmonic generation where the crystal melts and halfway through, right, and turns off. So it's a way to think about what happens. So that's so far the summary. Now you remember this image. I want you to remember it well. because it's the interference between the state that came from the bond and, or if it's an atom, the orbital and the electron that comes back. And you remember that the charge goes back and forth by that interference. Okay, so we already know something about the size of the bond, if you like, or the underlying ground state, because the interference is important is a cross term or it's an interference term. It needs both pieces in order to do it. And so if you look at the high harmonic spectrum that comes from the system, if you look at the radiation, the spectrum of the radiation, it tells you about how far the oscillation was. It tells you everything about the oscillation. And so you can do a tomographic image, which changes the angle and do just exactly like a medical tomography and get the structure of the material. Okay, so you can get the structure of the bond. You can look at the bond. You can look at the bond within some approximations, and we use approximation of optics, but it's not optics, it's electrons, and so they're pulled in a little bit. So there will be some errors, but approximately the structure of optics, and you can do tomography just like optics. And so I'll give you a tomographic image, and I just wanted to show you that it can be done. We all know what the bond looks like in nitrogen, and the upper image here is the experimental nitrogen bond. It's made from 19 different projections, just changing the angle of the nitrogen, moving around. 19 different projections using tomographic methods, just using tomography as you would medical tomography. It's the wave function, not the wave function squared. But remember, we've removed characteristics of the initial wave function when we make harmonics. So it's referenced to an unknown phase. So it doesn't violate what we know that there's no absolute phase. There's no absolute phase in nature, and there's no absolute phase here. We don't measure the absolute phase. We measure it relative to the bond, which is now canceled out. Okay? And the others are just different ways of calculating the bond. Okay, so now we've got high harmonic generation and attosecond pulses to a certain extent. I want to say more explicitly how to make attosecond pulses. There are now multiple ways, and so I will only give you one, because all I want you to do is understand the idea, and you can probably come up with multiple ways. So one way is to make the pulse that drives it only a single cycle long. Now you can say, how could you ever do that? But modern laser technology is really, really, really good. And amazingly as it sounds, we can make pulses that are about one cycle long. And I show you it's not an autocorrelation trace. I know it's done in our lab. I don't think I think it's a frog trace. And that's the square of what we can make for a single pulse. You can see that there's one prominent peak and there's two others, and so it's distorted somewhat, but it's sort of like a single cycle pulse. So if you can make a single cycle pulse, nothing much happens in the first little bit, and you can make it so nothing much happens up here, nothing much happens here. Maybe it starts to ionize there. And of course, it's accelerated away, and now it's accelerating back, and it collides and makes the attosecond pulse here. Of course, even more, the atoms will ionize there, and they accelerate away with a strong field. They're pulled back with an increasingly weak field, and if they collide weakly, and you can just filter them away. And so you can make an isolated attosecond pulse with a single cycle pulse, which is just an interference. I told you before. You can make an isolated attosecond pulse with a single cycle pulse from a laser, and I'm sure people do it here, and people do it all the way around the world. There are other ways. I don't mean to say it's the only way. It's not the way we're going to use. And a little bit later on in Ottawa, so it's another possibility. I'll just say how we're going to do it. Is you can make this part circularly polarized, and this part circularly polarized the other way. And this part linearly polarized, so circular, linear, circular the other way. So going the other way. And it's possible to make with wave plates and dispersion. There's a number of ways you can go ahead and do it. And so I could talk about it, but I'd say it's more complicated. It's easier to see a single cycle pulse, and the single cycle pulse makes a single burst of radiation. And I've told you how to put all the colors together. Okay. So now I think you know you know everything there is to know about attoseconds. There's a quantum mechanical version, and I'll go to the quantum mechanical version for your intuition in a minute, but I won't do it yet. Um, so I've largely talked about atoms, and you might say it's a characteristic of atoms, and that's largely what the community thought at first. It's a characteristic of atoms, but it wasn't true. It took about 20 years for people to look carefully at transparent solids. And maybe here and there in between, especially theorists, talked about transparent solids and making high harmonics, but nobody took them very seriously, if you want my opinion. So, but it was about 20 years ago when the first, maybe a little less than that, when the first person from basically our community started to look at them carefully, and we all believed that there was harmonics from transparent solids. So now you could make high harmonics in gases and transparent solids, and at least you could imagine doing almost anything you wanted. You can make it from glass. People started to make it from glass, from water, so it's liquids, from transparent materials in general. There were two other mechanisms that could be involved, and I'll mention both of them. I'll mention both, but one is definitely involved. One possibility is what's often considered block oscillations within the community. It's not really a block oscillation. But the atoms in a solid, a crystal, are regularly spaced one after the other. And as the electron comes up and gets increasingly accelerated, it can see these atoms a bit like a grating, and it gets reflected back. In fact, that's the origin of block oscillation. And that's, in other words, the atom, the electron sees the band structure of the material, and it can only live within that band. Of course, it can jump to another band, but largely it's interesting to think about them as only two bands, the conduction and valence band, although jumping is possible. So block oscillations, or the band structure of the material, can play a role, and it tends to limit the harmonics to lower values. But still the same idea. Electron comes back and recollides. It's possible that there's another idea involved. That is, the electron no longer, it must stay on the band, so it doesn't necessarily have a sine wave, and you can make it up of multiples of different sine waves. And that may play a role. It's hard to say. In some things it plays a role, some things it doesn't. And I personally think most of the transparent solids are electrons coming back and colliding and recolliding. Also, in a solid, you have electrons that move, and you can have holes that move. That wasn't possible in something like an atom. Well, maybe it is, and that will be the last part of my talk. But in an atom, largely you don't think of electrons moving, but the holes definitely move, and so it's not only the electrons, but the holes play a role. And so what you thought about for solids, you have to add the electrons and holes together. Okay. So let me just summarize that part before I go on to the final part of my talk. And so, so high harmonic generation is a universal response of materials. It's atoms, gas molecules, it's condensed media that are transparent. And now there's work in my lab and maybe other places as well that show you can get high harmonics from solids. And the mechanisms are related. Sometimes it's the oscillation of the charge, which is not sinusoidal, and sometimes it's a recollision. And probably all material before it damages will do this, I think. That's what I think personally. In solids, in new materials, high harmonics are being used often as a diagnostic of the material itself. Um, you can sort of, if you think of it as two bands, you can reconstruct the band differential, for example, only from the high harmonic spectrum and things you would measure in high harmonic spectrum. So it is one possible diagnostic of a new material, and it's being used that way. Um, we must generalize from holes and electrons must be included because both move. Um, they lead to attosecond pulses. Um, Mainly it's done in gases, the real true attosecond pulses, because the spectrum is limited in solids. The state of the art is 40 attoseconds. I think I've already said that. Usually gases are used. And pump probe spectroscopy is possible with these pulses that irradiate out just like a laser beam, although they're created in a different way. Usually, however, they're kind of weak relative to what you can do in free electron lasers and other things, and they force on this field that you pump or you probe one or the other with the attosecond pulse, and you use visible or infrared radiation for the other part. But within that constraint, it's used quite broadly. Now I want to ask, is there a hybrid between what we've known for gases and what we know for solids? Can we find a hybrid? And so I want to use the atom xenon, which has a weakly bound 5p electrons. It has many other electrons, of course, down below, and is xenon useful? So I want to talk about xenon. It'll be slightly more specialized than the other. I'll speak to the more specialized people. I hope it can be understandable to everybody, however. So one thing you can think about is what happens to this recollision electron in xenon. In xenon, the 5p electron, the p electrons are located about an angstrom, the lobes apart, and the 5p electron. And the recollision electron at about 100 eV, is as I show it here. I show it with the plus and minus and an X, well, that's not an X. I show it in the oscillation. And so you can think of the oscillation between the 4d electrons, which are done in sort of a circle in the middle. And you can think about the 4d electrons as a circle in the middle, and then being interfered with the wave that you see up there, which has the wavelength of a 1.23 angstrom source. And these are roughly scaled as they should be. Of course, it's not 1.3 angstroms across on the board, but then the relative circle, the red circle, the plasmon, is approximately right. And so the interference of the 5p electron and the electron that came from it, in other words, what would allow us to look at the structure of the orbital of the 5p electron, leads to the oscillation, which is what an oscillation like this, back and forth, back and forth. Just think of the interference between the wave and the p electron, which has the same symmetry of the wave. It goes back and forth, back and forth. And what that does is pump the motion of a plasmon in the center. So now we go and we interfere with the core of electron, which usually we can't have much to do with in optics, but we interfere because of this interference with the core of electron, and we started oscillating. Actually, this is known from synchrotron physics from a long time ago, and it leads to this huge field in the center of the atom. You can estimate it at about 500 volts per angstrom, which is really large. We don't usually deal with laser fields of this kind of size, or even close to it. And excuse me, what was which? The recollision electron creates a pretty charge on the right slide. Oh, I think it's a mistake. I don't know. But it's really, it creates almost an ideal. It's a mistake. I just didn't correct it. I'm sorry. I didn't correct it. I didn't see it was there. I think what I meant is if I wanted to excite these 4D electrons down in the core, what would I do? I would try to find an oscillation that would go with the electrons and make them move and just try to be resonant with them. And so this creates an almost ideal excitation mechanism. It's meant to be ideal, I think. So I'm sorry not to have noticed this. I didn't notice it. I probably changed it last night, which is usually a bad idea. So anyway, so I want you to think about that this in the center, there's 10 4D electrons, which tend to move together. They tend to move together. They tend to move as a block. And so you can think of them as a plasmon, and we found a nice way to make it to excite them. So now let's start zeroing in on this plasmon. So I've taken the picture that you saw at the first of it, and I want you to remember back to that time. And I want you to remember the ionization of the electron and how the electron goes off and comes back again and collides. And that's the case for one possibility in xenon. But it's been known for a long time that there's another possibility in xenon. Xenon has two levels in the ion that are relatively close together. They're separated by 1.3 eV. And so there are two levels in the ion. And maybe I can ionize from both of these levels simultaneously and create a wave packet. But then I leave a wave packet behind in the atom. It's not any longer a single active electron. There are now more than one electron. Let's call it two, because there's going to be a hole created by this thing to allow the hole to move around in the atom. Okay, this has been known to xenon for a long time, so I'm not telling you anything new about xenon. And it's been known that when you ionize in strong laser field like this, you ionize from the downhill lobe. You don't ionize from the whole p orbital, so you ionize from a superposition that allows you to have the downhill lobe. And so you can think about it as it creates a hole in xenon. Now, I'm not telling you anything new. It's been known, that's been known for some time. I just want to reemphasize that's been known for some time. Nobody has thought about what it ultimately means, I think, for xenon and high harmonics. So I want to tell you and end up with that. So of course, what happens? One case, nothing happens. The ion stays fixed. There was only one level. Ionized, I could do everything I talked about before. But in the other case, the hole moves around in the atom, and we know everything about the hole moving, or we know a lot about the hole moving in the atom because we know the spectroscopy of the ion. And so it moves around about in the ion, okay? As the free electron does exactly what I've talked about before, over and back, colliding and giving us a burst. So can we understand anything about that? So we did an experiment in which we measured the attosecond response of the material. I'll tell you about how the experiment's done next. But let me tell you first about what we see. So along the horizontal axis is the time measured by the cosine omega t and coming back and colliding. And on the vertical axis is the frequency. And we see a mechanism that first I want to point out the part that I described to you before. Remember the chirp that I started out with? It started in red and it went green and then blue. And that's the chirp in reality. That's the time on the bottom that it's emitted and the frequency is emitted. And this is the chirp in reality, and it's exactly what we expect. So it's exactly what I've told you about before. However, we see this radiation at 85 eV that it must be wrong, right? It's 3 picoseconds. There's no recollision of any energy at 3 picoseconds in the cosine omega t. And so if you want to think, you can think of that in a time. So I convinced when I first saw this as the supervisor of the project, the student did it, Dong Ko, his name was, and I was convinced that this was wrong. we must be making a mistaken experiment. Nothing in the core comes early, and nothing should come a femtosecond early. I was convinced we were wrong, but he went back and he redid the experiment in all kinds of ways. And let me try to tell you now how we did the experiment and give you the idea behind it. Now, I've described to you about how ionization occurs and how you can measure the electron. I said, let's imagine we did photoionization and we took an electron away, and we can put on a field now and measure how much the electron deflects or how much its added energy, depending if I put it on this direction or this direction. And use that for streaking, or there's a number of different names we give it. But I can do exactly the same thing with the electron that comes back and recombines. It does the same thing. It just does the same thing in the opposite direction. Goes out or come back. So we use the recombination electron, but we bring another field in and modify it. You can think about we do interferometry, and they don't obviously do interferometry. So it makes it a lot easier. So that's what we were doing. And this is the mechanism by which we make the measurement, basically. We bring the fundamental beam in, 1.8 microns. We bring a weak beam because we only perturb, created grating in the medium. We diffract off this grating, and we pick up all orders from the grating and look at it. And we project it back onto the medium. So in other words, we see the grating and we see when it's emitted. And so it turns out to be a mechanism that's used all the time in short pulses in frog, and you may not know it here in the audience, but there's a mechanism by which we measure amplitude and phase, so where the grating is at the phase. We measure amplitude and phase and thereby construct a full pulse. Frog is frequency resolved optical gating. So it's a technique used in ordinary laser physics all the time. And it's considered, I think, the best technique. You characterize fully a pulse, amplitude, and spectral phase. I could tell you about frog, but it would take me quite a while. So sorry. It's in this field, you tend to give measurement techniques one of these cutesy names. So frog, I think, started this out. So people think of this as a frog, frequency resolved optical gating. There's rabbit, there's all kinds of these things. Spider, I mean, you just have to, if you like that kind of thing, it's good. If you don't, I don't particularly do it. So then we started, so then after a few times, we started to take it seriously. We also developed theoretical models, density functional theory, which I won't tell you about here. And that gave another reason to believe that maybe it was serious. So the first time we reconstructed a pulse, we saw this dip in the middle of the pulse. You might see that I say the 3/4 spin under a certain time, and that was where the wave packet should get to 3/4 of the way around, not all the way around at that time. So we know exactly that time from ordinary spectroscopy, and we could see the spin wave packet. So probably this was true. Let me talk a little bit about this now, okay? We see, and the most prominent thing you see is an interference. And that interference comes from the fact that at that early time, we had radiation of two frequencies, one about 30 EV and one about 85 EV. And they couple together and they give you a modulation. It's like a beat in a musical instrument. We're seeing the beat between two different frequencies of radiation given out at the same time. 30 EV, 35 EV, and 85 EV. It's confined to 300 attoseconds. It's confined by spin, and the spin goes the wrong way at the time, or it's possible that it's probably the spin is the wrong direction at the possible at the 3/4 time. We see that in the single active electron, and we see it in the double electron. And so that's the two characteristics. If we take out spin in a model, then it just continues without that dip. So then we had to take it seriously. Okay, so the next thing we did was we tried to take this plasmon, because we figured everything was a plasmon. Let's take the plasmon and try to treat it well. And I'll tell you where we think it comes from. And then I don't think you'll ever forget it if I tell you that. So the plasmon, we said in many areas of science and molecular physics, you may have come across it yourselves. In molecular physics, we often approximate a plasmon by taking a sphere of metal at the same radius, or maybe just slightly above the radius. You can treat carbon-60 that way, and it's almost exactly correct. For example, because there are lots of pi electrons that move around pretty easily, and you can treat carbon-60 that way. And there are other things that maybe it's used in atomic physics. I don't know of it, but maybe it's used in it. So we treat it like a metal. And we said a metal in a field of like this, we can estimate. So what do we estimate? So we'll estimate the Stark shift, that is a shift down. And it goes like E squared. So I want you to just remember this. It goes like E squared. I think Stark shifts always go like E squared. E creates the dipole, and E squared creates the dipole shift. The dipole now interacts with E to give you a shift. So it's always an E squared. And so when there are two components of the field on this, the field of the hole or the field in the core. It doesn't have to be only the hole that's moving around. It's the field in the core that the ion sees, plus the field of the laser. You always get something like E squared, where E is E of the hole and E of the laser. And that always gives the first order term that's laser related of 2 E laser, E hole. And so that's how we think we get the process. That's how we get the shift. So that's just taking the same thing and now putting it in terms of a shift. The 2 comes from the expansion of the term, and the 4 comes from the fact that you always get a stark shift up. You move the upper level up and the lower level down. Okay, so that's the only thing that's added in there. So now let me show you what happens as a function of time. So first on the right is a sketch of what we see, picking the center of each. Well, actually, the top is, I think, the edge. This is something that's just undergone what we're doing now in the lab, but this is basically correct. And if you add that distance, where does the extra energy that we picked up from the laser that wasn't there for the single active electron? There's 44 eV down at just over 3 femtoseconds and 28 eV and 11 eV. And if we take that from the delta E term to 4 times E delta E, it actually works out. So there's the fit that comes in with that term. It's not only that, oops, I'm going the wrong way. It's not only that, we, we can look at the fit of other structures in here. So here we see two things. We see radiation coming down here. We don't really think of it. We don't really understand it really very well. But it turns out we can fit it by just assuming that there's been a cross and something does happens. We bring the two levels, or this part of the two levels, so that they cross and then they go other. And so we take 1/2, not 2, not 4, but 2 times r e dE times r cubed. And we can fit with the same parameters, by the way, as the other ones, every feature, or at least every major feature on this curve. So we think this is now got, it's amazing that it's so good. We think this is the essence of the explanation. I don't mean it's the full explanation. Full explanation will be a much better theory than this, but this, I think, catches the essence of what happens. I think it's very exciting, and it's very exciting. So let me just conclude in this. I think it's very exciting because it gives us a chance to measure core fields by using laser techniques only, laser techniques, and passively looking at the radiation that comes out. So it gives you the chance of getting 4 core fields. It also gives us a chance to make pulses that are confined in other ways, and so they're shorter. It gives us a chance to change the chirp on the pulse that you saw and the time that sequence comes out. that we can make the chirp, we can modify the chirp and the pulse, and this laser field and where we are in the laser field allows us to control this. And so it solves a number of problems that existed in Attosecond Science before. Okay, I'd like to conclude then with just a concluding sign. So I'd say that the motion of the whole, combines or unifies atomic and solid state physics. In solid state physics, the whole always moved, but of course, holes always move in solid state. It's nothing very important, nothing very significant. But here, the whole moves too, and there are probably other cases. We use entangled photons. I haven't mentioned that before. So how do we measure the time? We measure the time from the recollision electron. And we say that time is appropriate for the other electron or the other contribution for the fact that the hole comes up and the hole ultimately is killed in the last stage. We measure the three-quarter revival of the spin. I think this is the first measurement of spin dynamics in attosecond output. So we measure the spin dynamics in xenon. We presumably can do this in other materials. We roughly measure the core field. I say it's rough because there are things we don't know. We use the external field as true external field. I don't know, there may be some polarization that changes that. There may be other things that we didn't know, but just taking a sphere, a sphere through the peak, we just took the peaks of the D electrons are not spheres. So we made gross assumptions. So getting rid of the gross assumptions, I think, will allow us to learn internal fields and maybe use these internal fields for other things. Maybe we can push harmonics to shorter wavelengths in other materials. We extend the high harmonic cutoff. We propose that we could use square pulses. People talked about ideal pulses or maybe just third harmonic and place them where we want. So we have the field when we need it, and that can add to the field that's we're stealing from the core. Okay, so maybe we can extend the high harmonic cutoff. We can probably control the chirp because of the falling laser field. So the chirp is just, we can probably compensate for chirp. So it's possible at least. We doubt that a well-established plasmon is the only identity in the core, but we don't know for sure. The core is not known, and certainly it's not my specialty. This has come up. So it could be that there are many things in cores that we can look at or exploit. I don't know. We doubt that this is a well-established plasmon is essential, but we don't know for sure. We propose that 30 attoseconds, the plasmon period, is the maximum speed of response of electronic matter. So I would like to I'd like to end with that. So there's a large group of people. I didn't do this experiment alone, of course. And Dong-Hyuk Ko, I noticed last night, I was kind of late to do anything about it, is up there right behind somebody's hand. So that's him who did the experiment. He's hidden. And he's a kind of a shy, kind of a quiet guy. So maybe that's the reason, I don't know. And so that's the group in front of the National Research Council building in Ottawa, Canada. So thank you, and I hope there's time for questions. And thank you.